Kids, if you remember the other day, we talked about fundamental theorem of calculus part 2. These are often taught in reverse order, and it says this: the integral from a to b of f of x d of x is equal to, do you remember what you do? Big F of b, big F of a. That's how we determine an integral. A lot easier than adding up the area of an infinite number of rectangles, correct? Cool, huh? Sweet. Oh, as I get 3 yawns all in a row, it's contagious. Look out. Do you remember what big F is? Yeah, where F is any antiderivative. Of little f. Now, part of you might be wondering, well, what's the big idea about any antiderivative? For example, you would say 3x squared. If that's f, what's the antiderivative of 3x squared? X cubed, right? Well, isn't that, I get that that's an antiderivative, but isn't x cubed plus 1 also an antiderivative? Like if I were to take the derivative of x to the third plus 1, I also get 3x squared, right? Or if I take the derivative of x cubed minus 10, I also get 3x squared, right? There's an infinite number of antiderivatives for every function. But the difference is that the constant really doesn't matter. You could just choose the simplest one, so to speak. Okay? We all good there? All right. So what about fundamental theorem of calculus part 1? I always have to have my book to make sure I get this right. I don't want to mess it up. If f is continuous on the interval AB, so what does that mean? We're going to draw it. Everybody okay with that? What does it mean to be continuous? Stupid definition. Draw without picking up your pencil. We all good? Then the function g we will define g to be this. G of x is equal to the integral from a to t of f of t dt. Oops, made a mistake there. Knew I did. I always mess up that notation. A to x of f of t dt. What is that saying? It's simply saying this. If I have a function f, then we could talk about another function, namely this function. We'll call it the function g, where g is the area function. Can you guys tell me what happens to the area if I drag x this way? Does it get bigger or smaller? What happens if I drag x this way? It gets bigger. So a function has values that change. This is my variable. It's kind of the endpoint of the area. As you move this, do you agree that the area is going to change? Yeah, exactly. So this function is also continuous. And it's differentiable as well. On the interval AB, and we have one more thing, and this is the big idea. big idea is this. If you take the derivative of the area function, if I take the derivative of the area function, do you know what you get? You get the original function right here. So what is the relationship between these functions? We say the derivative of the area function which the area function, we think of the same thing as the integral function. Okay, it's the integral. So the derivative of the area function, the integral, is the bounding function. The function that bounds you from up above. It's a really big deal. I mean, that changed the world forever. The idea of a derivative and an integral, and the applications are endless. You're going to find integrals in studies of economics. You're going to find it in chemistry. You're going to find it in biology. You're going to find all sorts of things, which is why they actually have calculus for economics. They have calculus for biology. They have calculus for physics. They have calculus for all these different topics because of the applicability. And you can take non-calculus physics. For example, our school right now, anybody taking physics? Okay, yeah. So within your physics course, you maybe introduce some general dy dx topics, but it is technically not a calculus-based physics course because 99% of you didn't have physics yet, right? So a lot of class schools that offer calculus-based physics, they would offer a block schedule where you take Calc 1 first semester, and then second semester you take calculus-based physics or AP Calc. Okay, so let's make what we just said super duper easy. Are you ready? Let g of x be equal to, so this is a function, the integral from -6 to x of f of t dt, where this guy is f of t. So what we are asked to do is evaluate g of -6, g of -4, g of -2, and we're going to approximate it to the best of our ability. But what it means is instead of an x, I plug in -6. And so as you look at g of -6, that means the integral from -6 to -6 of f of t dt. So if I look at 1, 2, 3, 4, 5, 6, I start at -6 here, and I go from -6 to -6, how much area do I accumulate? Yeah, in fact, you don't accumulate any. Suppose I change the x value, instead of a -6 there, suppose I change it to a -4. How much area have I accumulated there? 2 units. Is everybody okay with that? Now I'm going to continue to move. I'm going to move off to the right. I'm going to do -2. So -2 right here. What do you notice happens to the function in between -4 and -2? It drops below the x-axis. I'm going to color the positive area in blue, and then I'm going to do the negative area in red. Would you agree that these two little triangle pieces are going to cancel each other out? So what is the area I've accumulated in total then? 3. I'm going to continue to move to the right. I'm going to move over to 0. Am I accumulating positive area or negative area? Negative area. So I've got another -1, got a -2, a -3, a -4. And I'm going to say that these two together make -5. Can we say that? Okay, we're kind of estimating here. So if I've accumulated -5, then what is g of 0? So -2. Because you gathered 5 negative values on top of the 3. Okay. Do you see that being 3? So then I have a small triangle of positive area and a small triangle of negative area. Those are going to cancel each other out. If the area sits above the x-axis, it's positive. If it sits below the x-axis, it is negative. Okay? All right, now we're going to move on over to 2. Do I accumulate positive area or negative area? Negative area. How many? -6. What's that going to bring me to? -8. Then I'm going to go over to 4. Looks like I pick up 1 more negative. We'll say 2 more negative. And then would you say that these two kind of cancel each other out? Yeah, so I picked up 2 more negative, which is going to bring me to what? -10. And finally, I'm going to do g of 6. So I go on over to 6, and I'm going to pick up area. Is the area going to be positive or negative? Positive. So what would you estimate that positive area to be? 3, 4, 5. Sure, about 6. So that'll bring us to about -4 then? Okay. Everybody okay with that? So this is your opportunity to pick up some really insight points that could help you on the AP exam. Some of you might get it, some of you might not. We'll hold on, we'll see where we get. Let's understand 2 different ways. It says on what intervals is g of x increasing? G of x is the area function. Agreed? So you tell me as I move along here, am I picking up positive area or negative area? Positive. How about here? So would you agree that I'm increasing and here I'm decreasing and here I'm increasing? Everybody agreed? Okay, so we're going to look at 2 ways. You did very good to understand that first one. So increasing from -6 to what? -2.5? Union with 3.5 to 6? And then decreasing from -2.5 to 3.5. Okay with that? Okay. Now, we're going to help you think of this in a second way, which should really, really help you make some connections when you take the AP test. This is the derivative, f prime. I'm asking you, call this -2, we'll call this +3. If this is f prime, where is f, the original function, decreasing? Why do you say that? When f prime is negative, the original function is decreasing, right? So this graph tells you something about the original, right? Because this is the derivative, right? Well, right now we're talking about g of x. What is the derivative of g of x? What's the derivative of the area function? The original function. So as it says, at what intervals is the area function increasing? Well, wherever the derivative is positive. The derivative was positive here, right? And the derivative is positive there. It is negative down here. So you can look at it that way as well, which really helps. Where does g of x have a minimum value? Well, remember, how about this one? Where does f have a minimum value? Is the minimum value at -2 or at +3? Which one is it? Why is it at 3? When f prime changes from negative to positive, you have a minimum value, correct? So if we're wondering where does g have a minimum value, we're looking at where does the function change from negative to positive? Where does this function here, f of t, change from negative to positive? 3.5. And if you look at our data that we gathered here, yeah, it's right between 2 and 4 and 6, right in this area here, that we get our smallest value, right? We get to -10. Excellent. It says sketch a rough graph of G. All you would have to do is take these points here and begin to plot them and see what it looks like. So for example, G of -6, you would plot 0. G of -4, you would plot 2. G of -2, you would plot 3, so on and so forth. Could you do that? Make a gentle sketch. What's that? This is F. The area collecting is G. Then we would plot -2 at 0. And we would plot -2 at, or -8 at 2. Kind of falls off the graph, doesn't it? Like you kind of see the shape that you're getting in general. It's not a real pretty shape, but it's, you know, it's something like that. It ends up heading back up. G of 6 is -4, so on and so forth. But you get something kind of like that. Okay? Ready for something easy? Let's do something easy. First of all, it says g of x is equal to the integral from t to 0. It's x to 0. Change that to x. My bad. This is the second part of the fundamental theory of calculus, part 1, and it is the easier part. It simply means this. If I want to solve that equation, what would you do to both sides? Because those are inverse operations. Agreed? Suppose you had this. E to the x is equal to 5, and you want to solve for e, or you want to solve for x. What would you do to both sides? Take the natural log, because those are inverse operations. They cancel each other out, right? Suppose you had x squared was equal to 12. What would you do to both sides to solve for x? So you were taught that these symbols just cancel each other out. They are inverses, and that's been ingrained in your mind over time. We'll do one more. Sine of x is equal to 0.3. You would? Sine inverse, right? And so those go away, leaving you x is. So you've learned about these inverse operations, correct? Well, here's what I'm telling you now. If you have an integral from 0 to x of, say, we'll say 4t squared dt, and you want to take the derivative of it, here's what I'm telling you. The derivative and the integral dt thing, those are inverse operations. They make each other go away. They make each other go away. And they simply just cross each other off. Okay? So as we look at this example right here, it says, if g of x is equal to the integral from 0 to x of the root of t plus 3 dt, it says, find the derivative of the following functions. We're going to find the derivative of this guy. So we're going to take the derivative of it. And when we do, the integral goes away, the dt goes away. What are you left with? Square root of t plus 3. The only difference is you plug in an x. X plus 3. I'll show you why in a second, okay? Just trust me for this one first. Yep, that's it. G of x is equal. Hey, it looks really complicated, doesn't it? Like, g of x is equal to this guy, and you want to take the derivative. So I'm going to take the derivative of both sides. The question is, what's left? Well, this goes away, and what am I left with? 3x squared, secant of x. That's it. Thank you. I never had a good explanation for it until now. We'll show you very simply. Watch. Integral, 0. Actually, we'll go from 2. 1. Go from 1 to x of 2t dt. Okay? All right? And what we're going to do is we're going to take the derivative of that, right? We're going to do it a different way instead of this little shortcut way where stuff cancels. I'm actually going to find the integral of this, okay? What's the antiderivative of 2t? T squared. And we're going to evaluate it at x and 1, right? And then I'll take the derivative of whatever I get. Okay? Well, if I plug in x, what do you get? X squared minus, if you plug in 1, what do you get? 1. And you're going to take the derivative of that. Let's now take the derivative. 2x. You see that? So instead of doing that work all the time, we can cancel them out and substitute the x in. Ian, your question, why do you substitute the x in? Because when you set up the integral, that's what you would be plugging in right there. You see that? Good job. What's different about this one? The x is on the bottom. Here's a cool property. This is the same thing as if you switch the bounds, it makes it negative. Whoop. So in order to get the x back in position, you just flip them and make it negative. Now I'm going to take the derivative. G prime is what? Negative sine of x squared. Look at this one. Uh-oh, the bounds are upside down again, so I switch them. G of x is equal to what? Negative integral through to x. Good. So now I'm going to take the derivative. And you're going to get negative natural log of x. Not too bad, huh? Take out your calculator. It's interesting, but in mathematics, when we calculate area, you can actually calculate area forward, and you can calculate area backwards. Go into your calculator and type in x squared. And go second calculate. And grab number 7. Let's integrate from 1 to 2. 1, 2. 2.33. We all good? Now, watch what happens. I'm going to go into y equals. I'm just going to type the x again so I get a graph. Second, calculate number 7. And now, instead of going from 1 to 2, I'm going to calculate from 2, say that that's the lower limit, and the upper limit is 1. And watch what happens. It gives me a negative result. Do you see that? So when you flip the bounds, it changes it from positive to negative. It's one of the properties that we have about integrals. Okay? Good work. What's different about this one? Yeah. So instead of just having an x up here, we have a 2x cubed, don't we? Don't write this down, but I just want to help you understand. Suppose we had the derivative of sine of x. What would you say? You say cosine of x. Suppose we had sine of 2x cubed. What rule would you have to set up? The chain rule, correct? Yeah, exactly. So in this situation, we set up the chain rule as well, okay? And we say that the outside is the integral from 1 to u of 1 over t squared minus 1 dt. And u is this substitution piece. So what is u? 2x cubed. What is the derivative of 2x cubed? 6x squared. Okay, if I take the derivative of the integral from 1 to u of 1 over t squared minus 1 dt, what do you get? 1 over u squared minus 1. Everybody agreed? Oh, I'm sorry, there's a t on top. I didn't even see it. I'm sorry. Thank you. So I'll be u then on top. Yes. So I take the derivative of this, the integral and the dt goes away, and I put the u where the t's are. So what do I put in place of u? 2x cubed over, if I take 2x cubed and I squared it, what do I get? 4x to the 6 minus 1. And I have to multiply that by what? 6x squared over 1. So our grand total is 12x to the 5th over. Yeah. It's not too bad, is it? But at the outset, it looks super complicated. Which brings us to our final problem. We'll finish right before the bell, which is awesome. What do you notice about this one? Anybody guess what I should do first? Switch it. Very good. So g of x is equal to integral 2 to 1 minus 4x. Instead of negative, I just have the cubed root of the sine of t dt. I'm going to take that derivative. I can't just cancel everything off because I have the 1 minus the 4x. So what rule do I need to set up? The chain rule. Very good. So I have the integral from what to what? 2 to u of cubed root of sine of t dt. I got rid of the negative due to flipping it. What goes right here? 1 minus 4x. What's the derivative of 1 minus 4x? Negative 4. What's the derivative of the integral from 2 to u of the cubed root of sine t dt? Cubed root of sine of u. What do I put in place of the u? Times negative 4. It's kind of impressive, huh? Excellent job today. Way to go. For a shortened day. I'm so impressed with you guys.